So I would like to begin to thank you, Fernando, for hosting the wonderful special year program, and for Lucas and David for the very kind invitation. So I will start with a motivating example. So now I will draw three different shapes, the surfaces, a sphere. And I want to ask you a question. Is there a shortest loop? And the second one will be a dumbbell, but you squeeze the middle to create a neck. And then for a surface of different topology, a torus. So this seems to be a study example in many talks here, and we will bring it to a slightly different direction in general activity throughout the 2-hour talk. And the answer for the sphere, I think we all know there's no shortest loop. Of course, what do you mean shortest? But here I'm thinking about if you have a closed loop, and then there's always one direction you can push to make the length shorter. So locally shortest loop. So there's no a round sphere. And for a dumbbell shape, you can see the neck give you a shortest loop because you cannot push up.
About free loops or base loops?
Yes, sorry?
You're talking about free loops or base loops?
Right, that's a very good point. So I try to be vague now. Okay. Yes. So, and there is one. And in this example, torus, you see there are many shortest loop. You can have one here, actually many around the cross section, and also the horizontal section. So there are many. All right. So the shortest loop here, I will really mean this is a length minimizing closed geodesic, so not fixed base point, right? And what we can draw from this three picture is positive curvature will tend to make the length shorter. So if you have a surface with positive Gauss curvature, so that means there's no length minimizing closed geodesic. All right. But then we see from a torus. So torus, because the topology, you can always construct closed length minimizing geodesic, non-trivial one. So the example here tells us a torus cannot carry a matrix of positive Gauss curvature. Okay, so it looks like it's an abstraction whether a manifold can carry a matrix of positive curvature. And also I want to remark there's a rigidity result here is if there's a matrix on the torus with non-negative Gauss curvature, there's only one, it must be the flat one. And so here I draw the picture, you see definitely this is not flat matrix. But remember, you have a way to put the flat matrix on the torus just by identifying the side of square. Okay. So of course, this flat, it cannot carry a matrix positive Gauss curvature is also a simple consequence of Gauss-Bonnet theorem, because the total curvature has to reflect equal to a topological number, which is related to genus. And for the torus, you know the total Gauss curvature must be 0. But this observation has been carried over to higher dimension. I think that's a milestone result in this direction. by Shen and Yao. So they observe the similar idea carried out to higher dimensional torus. So they prove more general situation, but let me focus on the torus case. If we have an n-dimensional torus, n greater or equal to 3, and then it cannot have a matrix of positive scalar curvature. Oh, sorry. Okay, and so they use minima surface. So it will be a similar argument, but for the shortest loop, it's replacing by area minimizing hypersurfaces in this case. And also there's a corresponding rigidity result, which is from their result together with, together with constant Warner's scalar curvature deformation in 74. The rigidity is the only matrix which has non-negative scalar curvature is the flat matrix. So the flat matrix is Euclidean matrix. Again, it's a cube, but you identify the sides. And that matrix on the torus is the flat matrix. Okay, so I forgot to mention, so feel free to ask me questions and anytime. So I will give you a taste of their proof in dimension 3. All right, so I cannot really draw a two-dimensional torus, but let's try to pretend. So a three-dimensional torus is 3 copies of S1. So I have 1 copy of S1 horizontally, and let's imagine the cross section here is another 2 copies. Okay, so this is a 3 torus. So what their observation is, again, by the non-trivial topology, one can minimize surfaces, the area of surfaces in the homology class of this vertical cross section. So there's a non-trivial area minimizing surface sigma, which is homologous to a torus, and one can show it has non-trivial topology too. Okay, and then by its area minimizing, we have the stability inequality on the surface, which will imply, so or the second variation formula of the area, so this trick has been seen in many talks through the year, is you can find out what the total Gauss curvature of sigma is, and that has a lower bound in terms of the ambient curvature. So where G is a matrix on the torus. So there is a square of second fundamental form that has a good sign. So the total curvature is bounded below by the ambient curvature integral on the surface. And now if G is a matrix of positive scalar curvature, that implies this cannot have the surface sigma cannot have positive genus. So that contradict. Or you can say that contradict our two-dimensional example in the previous argument. Okay. So it's proved by contradiction. If there's a matrix of positive scalar curvature, and then it will contradict Gauss-Bonnet theorem. Okay. So the reason they asked the question, or they work on the question, is that related to so-called, I think that was a problem asked by a physicist. I think it's called Robert Garage. In about 70s, he asked a question. So why physicists want to understand whether a torus carry a matrix of positive scalar curvature or not? Because somehow it's a special case from some question in general relativity, whether torus can be our model for the cosmology. Okay, so Xuanyao, they took the observation from this purely Riemannian geometry question. They also use similar idea to answer a question in relativity, so-called the Riemannian positive mass theorem. So you see the years are the same. It's not coincidence. I will explain a lot later. And so what's the statement of Riemannian positive mass theorem? So the manifold in this statement will not be a compact manifold. It will be an unbounded manifold. And we'll give someone more precise definition later. So this is asymptotically flat. So for now, you can just think about, I have a manifold which look like Euclidean space far away. Inside, it can have topology, I don't care. But then the matrix defined on the manifold will very close to the Euclidean matrix outside a suitably large compact set. So that's what the meaning of asymptotically flat. And the matrix has non-negative scalar curvature. And then what can they conclude is the following two statements. So there's an invariant called the ADM energy, which is a number correspond to the matrix defined using the matrix. And that number has to be non-negative. And the second is if that number is 0, the only possibility of such manifold is Euclidean. So somehow this number we'll define later. That's a number to capture the difference from an asymptotically flat manifold being truly Euclidean flat. Okay. So these two statements look quite different from the Torus theorem and the Riemannian positive mass theorem. But there was a very interesting observation by Lohkamp. Somehow he has a procedure to compactify this unbounded manifold to become the torus type, assuming the energy is negative. So it's by contradiction. Suppose the energy is negative, then this theorem is related to the torus theorem. So in other words, the torus theorem. So let's see. Right, so these two theorems are related in the following way. So if you can prove the Torus theorem, then that will imply the positivity part of the positive mass theorem. So that's why when Xu and Yao they prove the theorem in higher dimensions, that will imply the Riemannian positive mass theorem in higher dimension too. Okay. So this is called Riemannian positive mass theorem because there's a more general version of it. And so this will be a special case of a more general positive mass theorem type statement. But this is very important, a very important special case. So in general, we were looking at not asymptotically flat manifold. But we'll call the asymptotically flat initial data set. So it's just a Riemannian manifold somehow carry additional structure. So before I write the definition here, I hope it's okay. I will write down what the general conjectural statement related to the positive mass. Right? So which will be a Riemannian manifold. Somehow you carry additional information K. So I just throw you a lot of terminology right now, which I'm going to define later. Right. So I didn't probably now every sentence, every word you see is probably quite technical if you haven't seen that before. But I try to write a way very similar to the statement Riemannian positive mass theorem. So here we were looking at some triple quantity, which I'm going to talk about what's that, which is so-called asymptotically flat. And then with the dominant energy condition, that's another probably very strange term, and that was related to non-negative scalar curvature. And then the conclusion is the ADA energy, which is a number, again, is non-negative, but it's actually more positive. You're positive than some number, which is a norm of a constant vector. And that's related so-called the linear momentum. And with the equality holds only if this triple is flat, in the sense it's actually inside a Minkowski spacetime. Okay? Right, in Minkowski spacetime. And what this K really is, that means it's an induced second fundamental form. So somehow it's a way to tell you if you have a slice in some spacetime, and then what the rigidity is. If that equality holds, it actually tell you the spacetime is flat, not really the slice is flat. Okay? Right, so we will give a short terminology, call this triple initial data set. for here, you can just think about a way to say this is a Riemannian manifold carry a symmetric 0-2 tensor. But initial data set, in a sense, from generativity is, think about is actually correspond to a space-time. And if you have this triple, somehow you should evolve a space-time. So that's the initial data set for the Einstein equation. But here we are not talking about any space-time. So we are just thinking about it purely all the information contained in this triple. Right? Because whether it corresponds to space-time is called the Cauchy problem. That's also a quite difficult problem in wave equations. And then we'll call this initial data set asymptotically flat. Is, as before, the manifold has trivial topology outside a compact set. So topologically, it's just like an exterior region of a Euclidean space. And then the matrix, which will be very close to the flat matrix. And the K will go to 0 toward the manifold infinity. Okay. And then, what's the dominant energy condition? Dominant energy condition will reduce to non-negative scalar curvature in special cases. But generally, it means if we define this quantity mu, which related to scalar curvature, but also combination of the extra tensor K, okay. So the dominant energy condition using this notation means so this inequality, right? So quickly look, when K is 0, mu is just half of scalar curvature and J is just complete vanish. So this relation tells you the scalar curvature is non-negative. But in general, you have this quantity, and what this quantity is, this is a divergence of a 0-2 tensor, so this is one form. So to tell you, this quantity mu has a lower bound in terms of non-negative term, that's the norm of this J. Okay? Or you can write just another way. It tells you scalar curvature just by moving terms around. Tells you a scalar curvature has a lower bound. Right? But a very key thing which differentiates dominant energy condition from positive scalar curvature is the right-hand side is not positive in general. So you have a lot of positive term, but then you have a minus term, and the trace square can be bigger than the norm. This is a relation, but in general it could be negative. So that tells you we cannot really apply the techniques we available for positive scalar curvature here directly. Okay, do I define everything? Then what's the energy and the number P? So those numbers E and P are defined at manifold infinity. So they are just integral over large sphere, and then let sphere go to infinity. So in principle, they are just a number defined at infinity. So the bunch of numbers. And I think that's why it makes the rigidity part quite striking, is you have a number or bunch of numbers defined at infinity, but somehow if the number satisfies some equality, then it tells you the global geometry of the manifold. Okay, so let me define the ADN. Energy and the linear momentum. Okay, so this idea is named after physicists. So I think they define about those numbers around this year. And when they define it, of course, they immediately ask, if you want to call number energy, whether it's really non-negative, right? How the positive mass theorem came out after the definitions. So I will write down the definition of energy and momentum, but we will not really use the explicit formula. So the energy is a number you define by integrating some integral over a large coordinate sphere. So that's the integral defined on here. And now you make coordinate sphere larger and larger and larger. Okay. And there's a similar definition for the momentum. So it's a constant vector. P is a constant vector. Okay. All right. So probably I could easily lose half a U if you haven't seen those definitions before. But the good thing is you will not really need to know much about those definitions, except some special cases. So in the Riemannian case, what does it mean in Riemannian case? The Riemannian case is suppose the K, the extra two tensor is 0.
Sorry, the sum of the letters is just 1 index, I guess.
Yes, sorry. Yeah. Okay, thank you. So in the Riemannian case, we will think about K is identical to 0. And then everything involving definition of K will be 0. So energy is still there, but then the P, constant vector P, is 0. And also, the dominant energy condition reduced to non-negative scale curvature. So in other words, the general positive conjecture, in the case if we're assuming K is 0, that will reduce to the Riemannian positive mass theorem. Okay. All right, so there's some special, important special cases. So the first one is the Riemannian case. So let's solve by Shen Yao. And they also look the general case, not assuming K is 0, but the general initial data set. And they were able to prove by a totally different technique, so-called the positive energy theorem. Which is the statement, although there is a possible presence of P, but then they prove at least the energy is greater or equal to 0. So this is done by Shen Yao. 81. And with rigidity, if E is 0. Okay. So if E is 0, they can prove the initial data set is also embedded in Minkowski spacetime, with induced second fundamental form K. So the proof is three-dimensional. And so Eggemeyer was able to generalize the argument to higher dimension because the current development on a subject called marginally altered trap surfaces, which is a generalization of minima surfaces. So you can do that in this dimension. And there's also a complete different approach by Witten. So if M is a spin manifold, it's a differential topological condition on the manifold. Yeah. So this is So this is by Witten in 81. Okay. So there's also so three-dimensional oriented manifold is always spin. So Witten's proof will settle down the positive mass conjecture for the three-dimensional case. And also, still, his proof only have the E equals 0 rigidity. But somehow, the desired rigidity is stronger. So E may not be 0. It could be equal to some other number. But then, whether it's still true. So it's also, for spin manifold, there is a rigidity. Of course, there are also a lot of other progress which are important, but I'm not listing here. Okay. So let me state our results. So bottom line is we proved the positive mass conjecture in the low dimensional case, but it's in two different work. So first we have the positivity theorem, which we are able to show on the loss assumptions E is greater or equal to none of P. So this is in a joint work with Eggemeyer, then Li, and Shen. So the statement is just the statement of positive mass conjecture, but we do that for the lower dimensional case. So I will often abbreviate dominant energy condition in this DEC, dominant energy condition. Okay, so our proof is indirect. Suppose the equality false, then we get counterexample. So it doesn't show you what happened in the equality case. So that's in a separate argument. And that's a joint work with Stan Lee. All right, so that will be the same assumption. And so suppose the equality holds, and the only possibility is all those numbers are 0. And then we have the E equals 0 rigidity to show you the initial data set actually can be embedded in Minkowski spacetime. Okay. So I think I will pause a little bit for any questions, because I think I just threw you a lot of definitions. If there's anything unclear, just ask.
So this is like a hypersurface proof?
A hypersurface proof, so we don't assume it's inside any space-time.
No, I mean the...
Oh, right. Yes, right. Yeah. So there will be along the same idea. Use the extension of minima surface approach in this setting.
The
yes.
conclusion is actually stronger than what's conjectured, right? Because
It's actually, that's right, but yeah, that's right, very good point. So, but then if you know it's in Minkowski, then all those numbers will be 0,
okay.
right? Because those numbers are defined to be 0 on the model space. Okay. All right, so I think I will give you first just some examples of like what initial data sets, what dominant energy condition we really look at. So I have the first class of examples, which are the Riemannian case. Riemannian case, we're just looking for a manifold which has non-negative scalar curvature. Okay, so of course we have the Euclidean space. So Rn. And the matrix is the Euclidean matrix, and K is just 0. So then the dominant energy condition tells you the scalar curvature is non-negative, and it's definitely 0 on the trivial case. But then there's another important class of manifold that's called the Schwarzschild manifold. So that's found by Schwarzschild in 1960. Just very soon after Einstein's general relativity was published. And this is a class of manifolds which is non-trivial, but then is scalar flat. So we can write down the matrix that will be defined on Rn, which remove some ball and of the matrix, let's call GS for Schwarzschild, and K0. And where it's a family of a matrix because there's a parameter in the definition. So this family of matrix is defined in, so here I wrote down in polar coordinate. And so you can see this is a rotationally symmetric family of matrix, and with the possible to choose this number E. And by the definition of AD energy, that number happened to be the AD energy. So let's try to draw the three-dimensional case. So this will be defined over, I can make a precise of this radius will be. Right. So let me draw this. So somehow this only defined outside a ball of Euclidean space. And rotationally symmetric. So here, this picture you can think about is S2 cross some radius right, so each horizontal cross section is sphere, and this is a three-dimensional. Sure. Okay, and this stop if E is positive or greater or equal to 0. Right? So what happens if that number E is negative? So we want to prove the energy is positive. So look at the matrix. What happens if the energy is negative? If the energy is negative, that means there's no problem to define this term, because if E is negative for any positive radius. And the problem happens is at R equal to 0 at the origin is actually a singularity. But here, we will assume the manifold is complete. So there's really no singularity inside. And this is called naked singularity in relativity. So positive mass theorem tells you that cannot happen. Okay. And so this matrix has 0 scalar curvature. And E is energy. But then there's also, what do we care about general initial data sets? Because they do exist, right? If anything is Riemannian, why do we bother to looking at the more general case? So so the case K not equal to 0 can easily obtained. Okay. Right, so you can just looking at the Minkowski space-time, where this vertical direction is the negative distance direction, or people call the time direction. So the Lorentz matrix here is all right, now that we have a space-time and you draw any slice inside, graphical hypersurface, it will be an initial data set with the dominant energy condition. Okay, so you have many possibilities. And there's another important class of matrix called the Kerr solution. So the matrix can be explicitly written down. And which is quite many terms to write down. But the key thing is K is not 0. Okay. So there are those examples, and which tells you we cannot really just look at Riemannian case because it does not cover all the examples we know. Okay. All right. So I will take advantage of this 2-hour thing, so I finally have a chance to present some of the proof, because usually by this time I already done the definitions and we can close the talk. So I will outline the steps, and then I will give you more detail in next hour. So what's the proof? So as Fernando pointed out, this is the generalization of a minima surface approach by Shen Yao. And there's a really important guiding principle in Shen Yao's approach, which we have been talking about on and off, is positive curvature. So here is a scalar curvature is incompatible with area minimizing minima surface. Okay. So our general positive mass theorem is proven along the same guiding principle, but with the difference is we don't have positive curvature. We have dominant energy condition, but it's not positive. And then another difference is we don't have area minimizing surfaces. So I think it's a miracle that same underlying ideas still work in the setting. And the key thing is the scalar curvature in the general case is replaced by the dominant energy condition. And then what's minima surface is replaced by? So this is replaced by so-called the marginally outer trap surface, which is, in mathematical language, is a prescribed mean curvature surface. But more precisely, it's prescribed by the presence of the extra second fundamental from K, the extra tensor K. Okay. So there's an analytical difficulty to work on this. But then this equation is fundamentally different from minima surface. So this is called marginally outer trap surface. Okay. And the fundamental difference is those surfaces are not from minimizing some quantity. So minima surface, you minimize the area, right? Compute the first variation, second variation. But this is not from minimizing any quantity. So these surfaces are important in the sense is somehow probably first proposed by Roger Penrose, try to understand so-called the trapped region, which is the region of black holes. And then, so somehow they're looking at the surface which area minimizing along the null direction, the light direction. But now we're working on a slice of it. We don't have a null direction. So we do restrict on the slice of space-time. It does not obey any variational property. So this is the main topic I will present next hour. Okay? Very good point. It turns out it has a stability, which is also one key thing I will mention. Okay. All right. So yeah. So today I will talk about proof of positivity. So there will be the proof of this, the first one. Okay, and then, so I think I'm lucky I'm going to speak again in the workshop. So I will talk about the rigidity part there. So, so stay tuned. And the rigidity theory is by a separate argument. Okay. So let me outline the steps, and then we will have a break. Okay. So step one is we don't have positive scalar curvature, but somehow we want to have positive or strict dominant energy condition. We have strict inequality. So the step 1 is a deformation theorem. So I will probably give a little bit more detail later, but just let me outline the steps to summarize the steps. And the step 2 is, although we are given an initial data set, which is asymptotically flat in a quite general sense, but somehow we can perturb it to make a very specific asymptotics at infinity. And then the step 3 is in the 3-dimensional case. So the first 2 steps will give us the following conclusion is, suppose there is a counterexample. So it's by contradiction. Suppose there's a counterexample. What would go wrong? So suppose there's a counterexample, and that is okay? So the conclusion fails, the positivity fails, but all other assumptions hold. And then we can deform, so that will be really close related to the scalar curvature deformation. But so you can deform the pair G and K with street. So with the street dominant energy condition, somehow we have a street inequality to work on, and special asymptotics, the harmonic asymptotics. And you make sure all those deformation, they don't change the energy E and the momentum P too much. So it's still counterexample. So step 3 will start from this counterexample, and we want to get contradiction. So in the 3-dimensional case, we will produce a complete stable mods. Right? So we will define what the stability is for mods. It's very similar to the minimal surface stability. And it turns out you also have the same conclusion, is if you have a stable mods, then that will contradict to Gauss-Bonnet theorem. Somehow the stability will imply the total Gauss curvature of this surface. So this will be a surface. The total curvature is also positive, and that cannot happen. And step 4 is in the higher dimensional case. So now this conclude it's true in 3 dimensions, and now we do induction in dimensions. So in dimension greater than 3, we'll produce complete mods. So there will be a manifold, a hypersurface, which is open, a hypersurface inside the manifold N, and somehow with a stronger and what we'll conclude from this step is then we produce a counterexample in one dimension lower. So that contradicts to the induction hypothesis. So the base case is true, we're showing the n-1 case is true, and then in the case n, suppose it's not true, it will contradict to the n-1 case. So this is a general outline. Just let me finally, so these steps are very similar to the Riemannian positive mass theorem. So you replace the dominant energy condition by scalar curvature, and then you will replace the mods by minimal surfaces. But there is something different in step 1. So the deformation result to strict dominant energy condition is quite technical. So I don't think I write down that. But then it can be done. And then one of the fundamental difference is the step 4. Because we have to work on hypersurfaces which are not from minimizing any quantity. So it's already quite amazing. There's an analogous stability. But then there's a stronger stability. It really requires some new argument in step 4. Okay, so in the next hour, I will focus on only step 4. Mods. What's mods? Marginally out-of-trap surfaces. And also probably the key thing is what the stability, although in the lack of variation property. So mods will be some generalization of minimal surfaces. It will be satisfy a prescribed mean curvature equation. So we are showing is a two-sided, so we can define, there's a well-defined uninormal vector. Right, so this is called a mods. If the mean curvature is prescribed by the trace of the ambient symmetry to tensor restrict on the surface. This equals 0. Where here our mean curvature convention is for a choice of a normal vector. So this is sigma. So you can choose a normal vector, and then if that satisfies this equation, it's called mods. All right. And so the stability of minimal surfaces is coming from the second variation, right? But here we are going to define stability in terms of the first variation of this equation. So think about the mean curvature equation in the minimal surface case is from the first variation, and then the differential of that is the second variation. So here we will define the derivative of this equation to be the operator corresponding to be the stability operator. So how do we differentiate? We consider we have a family of probably surfaces and deformed from the normal direction, just for simplicity. And then we have a family of surfaces called sigma t. We can looking at this quantity, and this we will use the shorthand notation. It's called theta. And then we can compute this quantity for low loss family of surfaces, and then we differentiate And this will come up a second-order differential operator according to the normal deformation. So keep in mind, in the case K0, that will become the minimal surface Jacobi equation, because it will just be the linearization of mean curvature plus the linearization of other term. So the formula is quite complicated, but so you can basically ignore the term x. X will be some vector field defined. So actually, how about let me use W instead? Sorry about that, because I'm going to use x to be the deformation vector field later, so I don't want to confuse you. So basically, you can just think about W is a vector field defined on the surface sigma. And then the term Q, also quite complicated, but just because we want to somehow insert this mu and j from dominant energy condition in the expression, because there we have the dominant energy condition to apply. And all other terms are coming from the way to rewrite it and canceled out. But the case when k is 0, the Riemannian case, the W will be 0, so there will be no this term, no this term, no this term. And the only remaining term is Q, and Q will be half of the induced scalar curvature. Remember, mu is half the ambient scalar curvature. And this term will be 0, and k will be 0. A is the second fundamental form. So this recovers the stability equation for minimal surfaces. It should be, because that would just be linearization of mean curvature. So this identity probably was first really amazing. There are a lot of cancellation in computing this term, but let's find out in Shen Yao's the paper positive energy theorem. And then people use this quantity, this operator, to define stability later. So we'll call this equation using this shorthand notation L to be this linear elliptic, second order elliptic operator. And the stability of mods is being defined using the eigenvalue. The first eigenvalue should be non-negative, as the usual sense. And that's equivalent to this following definition. So it's defined to be, suppose you can find a function which is positive inside if sigma has a boundary, in positive inside, and then such that the operator acts on this function is non-negative. So in the case, for example, there's no listing if it's a self-adjoint operator. That's equivalent to say the first eigenvalue is non-negative. But then this operator is not self-adjoint, so there's this quantity, and the eigenvalues may be complex numbers, but this also has a corresponding to the so-called principal eigenvalue to be non-negative. But I will not introduce that. Okay, so this stability was later, I think, defined by Lars Anderson. Michael Mars and Walter Simon just recently, this 2000. So a lot of progress on Mars was just done in the past decade. So this is a very important observation is somehow the stability play a very similar role as the stability in the minima surfaces. So this is a one important example of how similar it is to minima surfaces. Okay. So it's a work by Galloway and Shen. So suppose the ambient manifold satisfies the dominant energy condition. So you can see the dominant energy condition will tell you this term has a good sign. Then, and suppose sigma is a hypersurface, which is a stable, is a hypersurface without boundary, so it's closed and stable mods. Then, so first, this stability-like inequality holds. So this will be very similar to the stability for minima surfaces. And from there, you can conclude by the dominant energy condition, sigma is Yamabe non-negative. Which just means it has non-native scalar curvature after a conformal change. So I will do this computation. It's a very nice, but on the other hand, probably you use similar thing in your research already, because it's also being used a lot in the literature. So the stability tells you there's a function phi, which is positive, because here we're assuming sigma has no boundary, and satisfy L sigma phi is greater or equal to 0. Okay, so since phi is positive, we're going to divide the inequality by 5. Okay, so we'll divide by 5, so this will be the zeroth order term just by itself, and this will have gradient phi over phi, so it'll be gradient log phi. And this term we are going to replace by the Laplace of log phi, and then add the error term difference back. So we'll get, so divide by 5, and then just let me move this divergence W there. Okay. So I move the divergence term to the first one, and then I will handle what's the Laplace phi over phi, and I replace by the log phi term, and there's a difference, which is one. And then there will be the term of right, and then there's the remaining term, this one. And I think there's really some miracle in this inequality. So you see, you can complete the square of this term, right? And so you get, also I combine these, both their divergence. So this is combining these two terms, and then complete the square. Okay, so now we want to derive this similar to the minimal surface stability inequality. You multiply a test function. So you multiply v squared to the inequality and integration by part. So if you integration by part, you'll get the divergence will be a gradient on the v squared with a negative sign. And then, so this will be on sigma. And all those terms we keep there. So this is minus. Okay, and then Cauchy-Schwarz inequality tells you, together with so just elementary inequality tells you can bound this term by v time I think gradient v squared, and then there will be v squared times the norm square of this one, which cancels out the term with the correct sign, and then with the remaining. Okay. So later we will look in the case when sigma has boundary. So I want to keep here, there will be a possible boundary term. Here, that's found by integration by part, but everything here is compute without using integration by part. Only here may come up a boundary term. If I have time to get there, we will see what the boundary term will be. But what can conclude here is we have Lat inequality, right, with a good sign. And then how is it related to conformal change? So now the rest is very similar to the minimal surface case. So once we have Lat, then we will see, we just write down what the term Q is. So Q has a term with its induced scalar curvature. And then you have other terms. You move to the other side of inequality, and all those terms has a variable sign, which will be mu minus, can be bounded by this one, and then with the sign positive of k plus a squared. So this computation holds for any v. That tells you this operator has non-negative first eigenvalue. So this operator. And then this operator is more positive than the conformal Laplace operator. So this will imply the conformal Laplacian. And then the corresponding eigenfunction can be used to conformal change the matrix to get non-negative scalar curvature. So this computation tells you stable mods somehow behave very similar to stable minimal surfaces. And then how about the existence? So if there is a stable mod, it's very nice. We can work on that. But how do you come up a mod to begin with. And this is probably one of the most different parts from minimal surfaces. The existence is quite hard. And even the plateau solution, fixed boundary, can you find the mass span lot boundary, was just developed, I think, about 10 years ago. Right, so I will not talk about detail. Originally, I want to talk about existence, and then I find I have to spend another 2 hours on that. So I will just give you some names. You can look it up. So there's a very beautiful. I think now we really know just one way to construct mass, and that's also in the paper Shen Yao in 81, where he proved the positive energy theorem, and then that way to find mass has been adapted in different situations. So there was so this is really the foundation of the existence, and there was proposal by Shen, and there's somehow really possible carry out that proposal, quite challenging. That's by Lars Anderson, Mexico. And the one we will really use is the existence of plateau solution of mass surfaces, as by Meg Ekman. Okay. All right. So I think now I will probably try to show you what we do in step 4, which will be in. Yes, please.
Give us some idea of how the stability condition come up in the existence.
Right. So it all comes from the Shen Yao proof. So they work on. So here is the manifold M. You want to find mass inside, but then they use I think very innovative idea, which of course due to John's physicist John, but for different purposes. They instead of solving the equation inside M, they're looking at the graph over the manifold N. And then they want to solve the mass equation of the graph, which is so-called the John's graph. And if it's graphical, then it's stable in this sense, right? Just like a minimal surface. And then, but that's on the one-dimensional higher space, right? So then the solution, the John's graph, is not always solvable. So the equation is not solvable, but it blows up. And somehow it blows up, will blow up to a cylinder, and the cross-section will be the mass of underlying manifold. And then in that process, it carried the stability carry over to the underlying manifold. So that's the only one way to find the mass of N, and the stability is because you solve the mass in one-dimensional higher space with stability, right? But it's also non-trivial fact. Okay. All right. Any other questions? All right. So I will try to tell you the idea of step 4. So it's already quite non-trivial to get stability, but here we want stronger stability. That's the point in the step 4. So let me probably formulate what we really need to prove in step 4. So what assumption we have and what our goal is there. Right, so we can begin with by step 1, 2 with a counterexample to the positivity, and which in particular has strict dominant energy condition and very special asymptotics and the equality field. And then we want to produce a one-dimensional lower hypersurface inside, which somehow can be made asymptotically flat with dominant energy condition and a negative energy. So that will contradict the n-1 dimension, which should be true by the induction hypothesis. And more specific, we'll actually construct the one with non-negative scalar curvature. And this will be coming from, we will construct stable mods inside N. Okay. Right. So now suppose we have the n-dimensional manifold M with energy less than P. We will assume just by rotating the coordinate, the constant vector P is pointing to the vertical direction just to fix a direction. Just by rotating the coordinate. And then, so we're looking at, so I'm going to draw the biggest picture I ever draw in my life. This will be the xn, the specific direction. And then we were looking at horizontal plane, which will be very, very high and very big. It's just like a plane. And this is of the height lambda. And then also horizontal part will be the remaining n-1 s1 to xn-1 coordinate. And those horizontal plane, we want to compute what's the quantity is. So this equal to 0 will be the mods equation. But then we compute for this will be a barrier. And we can see because we have harmonic asymptotics, I will not have time to talk about that, but let's just tell you we have a certain expansion of the matrix G and K, so we can compute this quantity explicitly. And this will be, let me just, so if I remember correctly, there will be some constant depending on the dimension, and then there will be the energy and momentum appear. And there will be the xn coordinate, and I think that will be x minus n, plus lower the term. So this is where we use the assumption E is less than P to begin with. So if this is negative, and that tells you with a negative sign, this is a positive. So this will be an upper barrier for the mass equation we want to solve. But then we can also take a one which is very, very low hyperplane. And then you compute. So I think we use the notation for this equation. And here the h is computed with upward normal vector. So you do the same thing, you find out, because you just choose negative coordinate, this term is negative, so it's a lower barrier, also with respect to upward normal vector. And then we can also take a very large cylinder. So probably let me use right? And then you compute with respect to, so this is with respect to this one, the normal vector is pointing outward. For the cylinder, we look at the one big continuous move. You may need to run off the corner, and the normal vector is here. And that will be positive, just because that will be the mean curvature of the cylinder. And the mean curvature of a cylinder in Euclidean space is positive with respect to outward normal vector. But the k will be very, very small. It will be lower the term. So that tells you we have barriers. So for each fixed height, so this will be the height h. So let me give a name. The cylinder C rho of rho very large is the shell of the solid cylinder. And then we can pick any height between lambda and minus lambda. That tells you this is in between. A surface here has positive theta, and this has negative theta, just like a minima surface case. That means you have a barrier, and then you can solve the plateau solution, and that's by. So you can solve a Motz span lot boundary. So that's by work of Eggmeier. And this is a stable Motz. Okay. And you can do that for any height between lambda and minus lambda. And the mass you get will also between this slab. It will not run away. And then what we'll do next is let radius go to infinity to get the complete surface, hypersurface.
Is this construction so far in arbitrary dimension?
That's right. So the dimension here is same as a minima surface. So here we restrict the ambient dimension to be less or equal to 7, so we guarantee to have a smooth Motz.
But would the construction go through with the small singular set?
Yeah, we'll go through. So it will just be, you will get the Motz with a Hausdorff with singular set of Hausdorff codimension. Singular set will be Hausdorff dimension at most 7. Yeah. Yeah. Okay. So then we take it, and we will get a complete hypersurface inside, which is still Motz, because the convergence will be in at least C2 sense, so the equation carries. And so this will be a Motz. But also, you will have this property. The induced matrix is asymptotically flat. All right, and you can compute the energy. Because this will use the equation k decay faster, so outside the large cylinder, it really will be the mean curvature equal to 0 equation. So you can solve it. It will be asymptotic planar with some good Tk. So it will tell you the energy of the induced matrix, because it's asymptotic flat, you can compute it. It will be 0. The only thing we don't know is what's the induced scalar curvature. So in general, the induced scalar curvature does not have a sign. Okay? But then we have a stability. Stability of mass on those each finite solution can carry over to the complete mass, and which will be, you consider the test function which are compactly supported. Okay, but that's enough. In a very similar fashion, tells you the property of conformal Laplacian. So that will imply you can solve the equation to the conformal Laplace. That means you can conformal change it. So there exists a function f on sigma which is positive. And it goes to 1 as infinity. And we solve the conformal Laplace equation. And here Cn is a dimensional dependent constant, which maybe let me write here. So this function can be used to conformal change the induced matrix. So what we have is, now we have a limit of those finite surface we call sigma infinity. And then with all those nice properties, because we want to get n-1 dimensional counterexample. So here we want to say is whether we can make the dominant edging condition, but it looks like we can do it just by conformal change the induced matrix. So we looking at after conformal change using that function f. So remember here it's just because we are working on n-1 dimensional manifold. Right, so it has 0 scalar curvature. Okay. So then what we have is again is asymptotically flat. Then now it's very nice, we have 0 scalar curvature. So to get counterexample, what we know is just what the energy is. So what's the energy? If you change conformally, the energy changes as well. But there's an explicit relation of the energy of this conformal changed matrix and related to the one you begin with by some term which involving f. So there's a phi n which is a positive constant. So what this really says is just we are looking at the intersection of the sigma infinity with the cylinder, with the shell of the solid cylinder. And then we integrate this quantity. So there'll be a flux, so this will be a normal vector to this, right? Okay, and this is 0. It will be really nice if we know this quantity is positive, then we know after conformal change we get negative energy, and that's a counterexample. So we will use divergence theorem to write this flux integral on the boundary to become the integral on sigma infinity. So you just take divergence of f and gradient f. But f we begin with satisfy the conformal Laplacian there. So we can replace the Laplace term by So now the question is whether this integral is positive. So it looks a lot like this one, because somehow, if you remember, this Q has a term of half of induced scalar curvature, and that will tell you the corresponding conformal Laplacian has positive first eigenvalue. But with one very subtle difference is here we are only allowed to plug in compactly supported test function. But then what's f here? F is not compactly supported. You approach 1 at infinity. So we can derive this, and that will finish the proof in the dimension n case, because we get n minus 1 dimension counterexample, provided the complete hypersurface sigma infinity has a stronger stability. So this inequality holds not only for compactly supported function, but also for function which goes to 1. So this looks like maybe just some technicality in this argument. Somehow, maybe you can get away just by using the usual stability to get approximation and to get stronger stability. But remember, in the two-dimensional case, let's realize on a choice of logarithmic cutoff function. And we know it's not possible. You cannot do that by clever choice of test function in higher dimension. So that turns out to be, the argument could just broke down because just one subtlety. Okay, but then what this corresponds to is in the minima surface case, that corresponds to we are not taking limit of those bounded surfaces of arbitrary height. That was done by we actually pick a particular height by looking at the surface of least area among all possible heights. And that extra step tells you somehow you know the stability also holds when you move the boundary up and down. So that enables you to plug in the test function which is 1 on the boundary. And that property carry over when you take a limit. So for minima surfaces, that's a height picking process. And that can be done because we know it minimized the area. So we pick the height which has even least area among all possible heights. But we cannot do that for mods because it's not variational. So that's the difficulty. At least I hope I convey what the difficulty is. It could be a very subtle thing. And it could be probably just you use totally different argument to overcome that. But then what we do is we actually define a functional which mimic the first variation of a minima surface. And that would be a boundary term. And that enables us to get the desired stronger stability. So probably I hope to use the last few minutes to just give you some idea of it. But before that, do you have any questions? Okay. So we will look. I will look at the daydreaming case. Just like hopefully, what can we do? Scenario. So we have a bunch of mods. Suppose they actually give you a nice foliation of the cylinder. So we will fix rho. So we want to the strong stability. We have to do that when we construct the bounded, the finite surfaces, not after you take a limit. You have to make sure that property already has when we looking at the plateau solution. So we'll fix a rho, and suppose we have those mods by solving each height is a smooth foliation of the cylinder. And then you can look at the first order deformation that give you a vector field. Deformation. Right? So which would just be a derivative, say, in height h. And we know because we pick that to be the particular mass of height h, and then we've moved h just vertically, so we know the deformation will be vertical on boundary. Okay, since those each one is a mod, so we know they satisfy this equation for each h. Now we differentiate. This is still true. And so what's this is true for any h. And then what it corresponds to is, so I have the computation we done earlier for for the Galois-Shen result, but this still works. It's the same computation here. So this, the right-hand side is the deformation of the derivative of theta. Now we have this equal to 0, right? And this phi will be, yeah, what's that phi? Phi is, now we have a foliation, and this is the first order deformation. We can decompose into tangential part and a normal part. Right, and phi is the normal deformation. Right? So the same computation go over. And now we can also multiply a test function. So all the computation goes through, except now we get boundary term because we have a boundary, and the test function we want to get will not be completely supported. So what's that boundary term? So this will be right. So this is by you move the derivative to v squared. So this will, boundary term will be v squared, and the inner product with w and minus log 5. So you get minus. So I want to keep the log 5. Gradient of log 5. And inner product with a conormal. And there's also a term of w, but it turns out that will be an error term. And here, this is the cylinder, and eta is the normal vector there. So if we hope a particular height to have the stronger stability, which means we want this term to be greater or equal to 0. Now we allow test function v to be non-zero on the boundary. Then we move this term to the left-hand side. What reduced to be proved is we want that boundary term to have a sign. So if we in particular choose the test function v to equal to the deformation vector field phi on the boundary, so that becomes so the conclusion is these two properties, this true for any height, and this true if we can pick a height such that this boundary term has a sign that will imply the stronger stability. And now the upshot is we compare to the minimal surface case. This term actually coming from the boundary term of the first variation. So now suppose we are doing the thing for affiliation given by minimal surfaces. And then sigma rho of H0 is the one of this area in H. So we can compute the deformation of the area. It's just a first variation of the area. And X is a deformation vector field. So you can do the same thing, decompose into the tangential and the normal direction. And the tangential part, we can do integration by part. They give a boundary term. And this term will be the mean curvature times phi, which will be 0. So this will be the boundary integral all right. And here you can also replace just because we know on the boundary x is the vertical direction. And the upshot is this quantity is exactly given by the derivative of this boundary term. So we define a functional on H, which will be the boundary term from the first variation of the minimal surface. And then this desired inequality will be replaced by, we're able to find a height whose derivative of log term is non-negative. Okay. Okay. So let's in the daydreaming scenario, you assume everything is smooth, you can differentiate. But the reality is it will not be differentiable in H in general, because even in the minimal surface case, they don't form affiliation. You may have non-uniqueness of a solution. The solution may jump. So we have to take care of all those derivatives, take into account of possible jumps of mods. And why you can find the height, which the derivative is non-negative, because give you probably just a last idea why it's possible is because we have a barrier. So back to the barrier again. So we know for this to solve the mod, it will be below the barrier. So what will be the normal vector, conormal vector eta? They will be pointing upward. So the inner product with the vertical direction will be positive on the highest height and will be negative on the lowest height. So then if it's smooth by mean value theorem, you know there's the one with derivative must be increased in some way. Okay, but we'll do everything in a more like a discrete version of it. Okay, so I think I'll just finish there. Thank you.